So again, welcome everyone. Today we are talking about the new statistical features that we have added in ARM in the last year and a half, 2 years or so. We have really two main features that we have to talk about. I have a couple of little slides at the very end in case we have time to deal with some of the other smaller changes, but primarily today, we'll be talking about our planned comparisons and equivalent treatments are the two big functions. And first up is the planned comparisons function. If you may also have heard of contrasts in just a little more statistical side of things, that would be another term that would match up to this same idea. And our overall goal for a planned comparison is that we can define a comparison of specific treatments within our trial. So we're really kind of creating a custom analysis in some regards with this functionality. And so the statistical engine, if you will, behind this are contrasts. And so these are statistical tests on a bunch of linear combinations of values that are coming from the data that we've recorded. And we'll dive into the details here. We kind of like to give some examples of why this would be used. So couple examples. If you want to compare one of your products to multiple checks or maybe multiple standards, sometimes you might want to have more than just one replicate's worth of checks out there. So you would have multiple treatment numbers assigned to the check, so that way you can have more than one check plot in a replicate. Kind of just the way you have to do it in ARM, since ARM kind of requires that balanced randomization and structure there. The problem with that is trying to analyze the data. Those two different checks tend to be kind of separate, even though ideologically they're the same entity. So this planned comparisons is a real nice way to be able to combine the multiple check treatment numbers that are really the same thing. We combine them and then compare that to another treatment. Another good use of this functionality would be to maybe avoid excluding some data. So, certain types of assessments or certain types of experiments, you're maybe not trying to set out to decide whether your product is better than doing nothing. So you might have such strong control in all of the treatments compared to the untreated check, for example, that it almost, having that check there in the analysis almost muddies the water, and it makes it harder to get significance in the treatment comparisons that we really care about. And so typically, your only option would be maybe to exclude that check or exclude a treatment that's highly variable, that's making the analysis worse than what we want. We kind of now have another way to work around that by just defining a planned comparison over the treatments we care about. And we still get to leverage the statistical power that we have by having another set of plots and all of these, observed values still in our statistics, but we are kind of focusing in on the comparisons we want to make. So that's an advantage for us to not have to just throw out a treatment that's causing havoc. We can just kind of instead just focus on what we want, but still utilize that data we collected. And the last option, if you have a multi-factor design, being able to set up contrasts for grouped treatments can be pretty handy as well. So let's just have a look in ARM here. I've got a screenshot from the trial settings dialog, and we have added a new tab within the trial settings, or also the protocol settings. Both of these will look identical, whether you're in a protocol or a trial. Of course, if you plan this in your protocol, then all of these comparisons you define will be copied into every trial that you generate. So that's probably kind of the best practice if you're designing these comparisons ahead of time to get them in the protocol, but you can add them in either location. So that statistics tab is new, and there is a table that it has the title of planned comparisons. And we can just, as we create multiple comparisons, if we choose to do so, that table will just expand and allow us to keep creating more comparisons as we go. You can type in, so in that comparison column, you can type in the comparison, probably more as you use this function more and more, you might kind of get used to the nomenclature that ARM is expecting. But certainly the first few times, we definitely wouldn't expect you to know right offhand how to write up the comparison. And so we have the little shortcut or drop-down button that has the little pencil icon. And that's going to bring up the wizard for defining a treatment comparison. So labeled here under number 3, just a way to kind of help guide you into creating a comparison. And it kind of gives us a menu, if you will, for the different types that we can do. We'll go through each one of these here in a moment, but that's the basics for just getting this into an ARM protocol or trial. Once you define those comparisons in a protocol or a trial, then as soon as there are assessment data for us to summarize, we can perform those planned comparisons simply within the AOV means table report, just alongside all of our other analysis. The only key is to make sure you turn on the option to include any planned comparisons. That would be in the AOV means table report options there, kind of towards the bottom. If you do have that on and the trial that you're summarizing has comparisons, then you'll see on the AOV report a kind of a extra table inserted right underneath your treatment means and mean comparisons. And that will be a table of all of your planned comparisons that you have set up. So for each comparison that you've created, the analysis will give us an estimate or that contrast value and a test statistic. So here the estimate and the T value or F value, depending on the type of comparison, is listed there for each assessment. And then we have a P value for the comparison hypothesis. And so that's kind of our final result. We can look at if that P value is significant. So if that's smaller than our alpha level, we would reject the null hypothesis, allowing us to conclude that there really is a significant difference between the compared treatments, whatever it is that we had set up in that comparison. Okay, so taking one step back to those list of comparisons, what can we do with this dialogue? What types of comparisons can we create? And there's really four different types. The first one here is a constant. So that's simply comparing one treatment to a specific value, a constant that you have that presumably would have some significant meaning to it for one of your assessments. So my example here, just the average of treatment 3, is that equal to a value of 100? Maybe if it's percent data, did it control 100% of the pest? Whatever it is, again, probably not super common, this constant example, just because you kind of have that hard-coded reason, that you're targeting the performance of a particular treatment. Might not be as common, but certainly is an option to create for a comparison. Moving to the next kind, the paired comparison is just a head-to-head, one-to-one comparison of one treatment to another. Is treatment 4 equivalent to treatment 5? Are those two, and of course we're testing, the null hypothesis would be that they are the same. If our alpha is strong enough, our significance, we can then declare that the two of them perform differently. We can also do an averaged comparison. So we could combine more than one treatment together and compare that against another treatment. So this ties back to one of our examples in the beginning with the multiple checks, or maybe multiple standard products. You can pool those together, get the average of treatment 2 and treatment 3, if those are the two check treatments in my list, combine all of the data from both of those together and compare that to treatment number 6, or the product that we're interested in comparing to. One of the nice things about defining a comparison like that, just at least with an ARM, is you simply put in the treatment numbers that you care about comparing. And an ARM kind of takes care of the rest. If you've ever done contrasts in SAS or another statistical program, you usually have to come up with the full equation. So, in our example where we've got two checks versus one treatment, if you're combining all the data from two different treatments, then you also kind of have to double the, you'd have to divide that by 2 to compare it to just the one treatment. So you gotta do the math and figure out the equation to make it all right, which is just not something you have to do in ARM. Just give us the treatment numbers. ARM will take care of how many treatments are on each side and get the math to work right. It's just a nice advantage where ARM's trying to keep it simple for us. One more type of comparison that we can do would be a pairwise comparison. So that would be comparing all treatments to one another. That's really kind of what we do already on the AOV. When you run a mean comparison test, or when you're running the AOV analysis, it's including all of the treatments in that assessment. And so you could actually kind of self-check that theory. You could define a comparison with all, a pairwise comparison with all the treatments in the list, and you'll see that the p-value from that comparison would match the AOV's treatment P of F. Just to kind of see the proof, if you will, of the math on this comparison side. But really the use would be, of course, to leave out certain treatments that maybe aren't of critical interest. So this ties back to our other example where we want to avoid throwing out data, even if a particular treatment isn't isn't of primary interest to us, or if that treatment is more variable and kind of causes havoc in our analysis. We can just create a pairwise of all of our other treatments and just leave out that one in the comparison. All of the data still gets used within this analysis to give us our result, but the comparison itself isn't making the comparison we don't need. It's only focusing on the ones that we do. So again, kind of the overarching purpose, reason to use this, I think, is really that's one of the more compelling reasons, is we can focus on what really matters. Not that there isn't a purpose to some of these other treatments in our experiment, but certainly to focus on what conclusions we might want to draw. We can really get more power, essentially, because we're doing that focusing in. Finally, here on this slide, I do have a note that for any of those 4 types of comparisons, you can add multiple phrases, if you will, into any one of those comparisons. And that just, kind of inserts a logical and operator to put in more than one comparison into a single test. So here in this example, it's kind of the multi-factor example here, where maybe I want treatments 1 and 2 are a light, kind of categorized as the light version, and I want to combine those and compare them to the medium designation. Maybe it's the middle level of formulation, or rate of application, or whatever. Compare that with, I think my screenshot's a little different than my medium 3 and 6. Maybe it would be medium to match the screenshot, and then the last 2, 4 and 5, we'll say, would be the heavy treatments. And so by adding these together, you do 1 and 2 versus 3 and 6, and 1 and 2 and 4 and 5. You could add a third one that would be 3 and 6 and 4 and 5, but technically, logically, it would be equivalent to just doing these 2. But that would be a way, just using the little plus button here on the right. Again, to make it easy, trying not to make it particularly complicated to write out a long equation or anything like that. Just trying to put an interface to that instead. And you can see above it that once you fill in the wizard, ARM essentially translates that into a somewhat simple string of text that really defines your comparison. So if you kind of get used to seeing how that gets done, you can certainly write this in the end yourself. But it's kind of nice just to use the wizard and make it easy. And then there's a description that you can put in to the right, and that description is what's used. If I go back 1 slide, I gotta go 2. That's the description that is put on the report. So however you would want to summarize what the purpose is, what you're trying to achieve with that comparison, use that as your description, because then that's what's shown on the report. All right, and I'm going to switch to ARM. Try to cover the whole thing in the slides with some screenshots, but just to kind of see it happen here in the trial, I'm going to go into my trial settings, and here's that statistics section. And I have my plan comparisons table chosen here. So I've already got 3 comparisons defined, but if I just use the little edit button, we can see what it looked like when I first created this first one. And so I can select whichever type of comparison I want to create. And there's just a little text reminder at the bottom to kind of give me a hint about what that means, what type of comparison I might be creating. We do also have a help topic that goes a little more in depth, mostly kind of covers what we just covered in the slides as a reminder as well. This first example was just a simple paired comparison, just one treatment versus another, and I'm simply typing in the treatment number. So I want to refer to treatment number 2 and compare that with treatment number 3. And so then I can write in my description whatever I want to designate. In this case, treatments 2 and 3 are the same product, just applied at different rates. And so this gives me the ability to focus in on that comparison. Is there a difference if we have a higher versus lower rate? I can just look at this second one as well. This is an averaged comparison. Our check treatment is treatment number 1. And now I'm going to compare that product that we're interested in. In this case, I don't care whether it was the low or high rate. Let's just combine that data together and compare it to the check. Say, hey, is this product, which is called tub, is that better than the check? And that's essentially what we are doing here with this comparison. Technically speaking, we're not getting is one greater than the other. Technically it's kind of a two-tailed look at things. If we reject this hypothesis that the 2 are the same, it doesn't actually tell us which one's larger than the other, but so the conclusion here is maybe statistically a little bit vague to say that, but in general, that is what we're checking. And then finally, this last one would be a pairwise comparison, but I've just left out the check. And maybe for fun, let's just add a 4th one. Since I claimed earlier, if you did a pairwise with everything, it's the same as running the ANOVA. So let's just do that. We'll do that comparison and just see if the results kind of match that idea. So that's how we kind of define the plan comparison. I do have some assessment data here, variety of pest severity ratings, and then a percent of check calculation and yield throughout here. Oh, and just real quick, we talked about the treatments, but just to show that there is that tub fungicide just at 2 different applied rates, and then our untreated check was treatment number 1. So to see the results, we will print reports. It is the AOV means table report. I'll just stick to the regular 5%, maybe student new equals least square. I just want to make sure to turn on our plan comparisons. And we can preview the report here. Try to zoom in so we can see. We'll just kind of look at, I guess our first two columns don't have much of anything happening. So we'll focus maybe on column 3 here. So right underneath our treatment table is our table of plan comparisons. So there's that description that we chose. Now for column 3, we've got our estimate, our t-value, and most importantly, we have our p-value. So for this first check of whether, our first comparison, whether it made a difference applying that product at a higher rate, our p-value is 0.5, so we were nowhere near close to rejecting that hypothesis. And so we cannot claim that those are significantly different, which matches what our mean comparison test told us as well. And we're not too surprised because they're pretty close together. We also compared the tub product, so 2 and 3 combined versus the check. Are those the same? And we do have significance there. So we can reject our hypothesis that those two are the same and say that there is a significant difference between the check and our product, which is good because we'd be in trouble if we couldn't say we did something, we were better off than doing nothing. This third one here was our pairwise comparison, just without the check. So basically we're comparing 2 versus 3, 2 versus 4, 2 versus 5, 3 versus 4, 3 versus 5. Every combination all wrapped up into kind of one holistic test here. And we end up with a p-value of 0.26. So we cannot really find differences between 2 through 5. But if we run this last comparison, which we think is the same as the ANOVA because it's the pairwise across everything, that is significant, which kind of matches what we saw here. Yep, doing nothing, that check was significant from everything else. But our p-value of 0.001, hopefully if we cheat down here to our treatment probability of F, 0.001, those are the same. We've got one more digit of accuracy here down in the treatment p-value. We only have 3 here, so I guess we'll have to guess or hope that is a 4 behind there. So those are the plan comparisons, and then of course you can see they just repeat for all of our assessments. Depending on the type of comparison, there might only be certain types of assessments that you really care about those results, depending on the comparison that you're making. But we do get that generated for each column that you choose to include on the report. So if you wanted to simplify that a little bit, you could always use the report option under the general summary. There's an assessment data columns option that typically would be set to automatic and just includes all assessment columns that have data taken. But in this case, you might want to select. So I could run the comparisons only on the particular assessments that really matter. And then I could have that report with all the plain comparisons. And then maybe I would generate a separate report that I'd leave off those comparisons if I wanted just the regular A or B or something. But that is really our planned comparisons. If you do want to dive a little deeper, we do have another presentation directly from our statistician. I'm definitely not going to show all of it, but just want to point out its existence. And it's linked here in the slides, which I'll share as the handout link when we send out the recording. To have the main PowerPoint, which has a link to this one. And so here you'll see you don't get too far before you get some statistics, some math, and quite a bit of it. It really just kind of talks through some of the ideas about why to use it, like we did in our presentation today. But then it does, of course, really dive into the math and all the equations that the ARM is doing. Also showing some SAS results to show, hey, what we get in ARM is the same as what you would get in other statistical programs. I like just to point out the mess of code that you have to create yourself for SAS relative to just putting in treatment 2, treatment 3, and off you go. But yeah, it just will talk through a variety of examples and the theory behind there. So again, that's just a link here to the user contrasts to take a deeper dive if you're so inclined. Any questions on the plain comparisons before we move on to the next function? Great. All right, so switching gears a little bit, we have equivalence testing is the other statistical function that we added. This one is more recent here, earlier this year. And so the idea with equivalence testing is in the existing AOV that we were just looking at in ARM, we get that mean comparison letters. And those, if you have treatments that have the same letter, that implies that those treatments are not significantly different. But that isn't statistically the same as saying that those two treatments are significantly the same or equivalent. And so the purpose of equivalence testing is to actually make that declarative statement that two treatments are effectively the same. So an example maybe of where you would actively be wanting to do this, perhaps you have a new formulation of a standard product out there on the market. And your goal is to claim that your new product is just as good as the standard. I don't have to prove that it's above and beyond better than what was out there in the market because my product is cheaper, or whatever advantage I have somewhere else. My only goal in my conclusion is to say that it is just as good. It is equivalent to this other product. And I can make that statistical claim. It's a stronger claim than this first sentence. If we just run an ANOVA and, oh, hey, these two had the same letter, so I couldn't declare significant differences, that's not as strong of a statement as the second one to say, hey, I have equivalence. These two are, indistinguishable in their performance. And I can claim that statistically with using these equivalence tests. So the first step in doing this is pretty important. You need to define how large of a difference is insignificant. So what, and so it probably, kind of pretty specific to, an assessment that you're targeting, if it's your yield in the end, if it's your control, whatever outcome that's of most importance that you're going to want to make this claim on, you need to define the amount of a difference between the two products that is truly not significant. So a few different ways to do this. You could do the percent of the treatment. So I guess to back up one half step, the two treatments that we're comparing, we're going to refer to your baseline one as your standard treatment. So that's almost the target that you're looking at. I've got, my product that I'm looking at, and then I have my standard treatment that I'm going to compare my product to. They're, in the end, they'll be kind of interchangeable in the fact that, all the math of what we're doing, it doesn't matter which one's which. But typically that's the thought, is there's a standard treatment that we want to compare a treatment to. So we could define a percent of that standard. So whatever the standard is at, what I would deem, what we would deem to be insignificant would be plus or minus 3%. That doesn't move the needle. If we're within plus or minus 3% of that standard, that's what we would consider close enough, if you will. You could also define that as a absolute value. So maybe it's plus or minus 5 bushels, whatever the unit of measure might be. If you have a specific value, you can do that as well. The third option, probably not as applicable, I think, in this industry, but would fit in general for equivalence testing, is the idea of your effect size. A variety of different, a few different ways you could calculate that. The one our statistician mentioned was Cohen's D, which you just take your treatment minus the standard, so the difference between those two, divide by the standard deviation, and that would be your effect size. I don't spend a lot of time on that one because it's pretty rare, I think, in most of the research done here with ARM. But for sure, your percent of standard and the absolute value would be pretty common ways to define. Again, really, you're creating this limit in ARM, your boundaries of what we would consider equivalence. And so you've got that reference treatment here that we're going to want to compare ourselves to, and we're just kind of creating this boundary above and below that reference, that standard product, that is this equivalence range that we're trying to target. Because if we can land our product in between that upper and lower bound, then then we're close to that product, and we can try to get equivalence there. And so then that is step 2. Once we have our range, we can perform a hypothesis test for this equivalence. And we would set up the null hypothesis being that the difference between our standard treatment and our product is outside this equivalence interval that we just set up in step 1. And we're hoping that we would reject that null hypothesis, because if we can, that allows us to conclude that the difference is inside the interval, which would mean that they are equivalent, that their performance can't be distinguished from one another. So in order to test that, we really have 2 different statistical tests to do. We would test if the compared treatment is less than that lower limit, and also is that compared treatment larger than the upper limit. So we kind of have to do 2 statistical tests, and if we can fail both of them, essentially, then we can say, well, the only other place that we could possibly be landed in is that equivalence interval. So in ARM, we call that the 2 one-sided tests, or TOST for short. So here's an example within ARM. Once again, we're in our trial settings or protocol settings on that new statistics tab. There's just a toggle instead of the plan comparisons. You can toggle over to equivalence tests. Kind of a similar structure in the fact that we have a table here where we can add different tests that we might want to perform. Our first example is, let's define our limit as 7.5% of the standard. So you would just kind of fill in this table here. The limit basis then, that's, how do we want to define our limit? That was step 1 a couple slides ago. So we want to specify a % of standard. So then the limit itself is that numerical value. What percentage of the standard do we want? And we're doing 7.5. That kind of provides our cutoff value. Then we define the standard treatment. So just like before, we're looking for the treatment number of what treatment we're comparing to. So number 2 is our standard that we're referencing. And then the alternative is the other treatment that we want to compare with. In this case, it's treatment number 3. And finally, we have a description. Just like before, kind of a nice way, open free text for you to summarize what we're doing here. And that'll be used on the report as well. Once again, you have to go to your AOV report options, and there's a little toggle to include the equivalence tests. So you can turn those on or off. Once you turn that on, kind of the same location as with the plan comparisons, it'll be a table right underneath your mean comparisons with these statistics from the equivalence test. So there'll be 2 p-values in this case, because we have the upper and the lower that we're performing. So there's the TOST, the 2 one-sided test. You've got the lower p-value and the upper p-value. And what we're hoping for in order to establish equivalence would be both of those p-values need to be significant. So we have a look at those 2, and then there is a nice simple phrase right here that summarizes those results. So in this case, the p-value for both of those were significant, and thus we do have equivalence being established. I forget some of the other phrasing, but depending on if you have the lower is not significant or the upper is not, or neither. There's a slightly different phrase there that just gives a nice summary of what you've achieved in some senses. Now there is another method. So we still have to have the step one from before. We always will define that limit of what is insignificant. But that step two, the method that we're actually using, we can either do the significance test, or here there is another option to use confidence intervals instead. Roughly we're doing something similar, but this time we're creating a two-tailed confidence interval based on that limit we're defining. So it's basically the same idea. We've got this upper and lower bound, but with the alternative treatment, we're really calculating an alternative confidence interval and comparing it with the confidence interval about the standard. That is our equivalence interval. If we can land that alternative, that other treatment we want to compare, if we can land that confidence interval completely within the equivalence interval, then we know for sure we have equivalence. So that's our hope, is if this is entirely within that, then we're good to go. If there's any overlap where some of this is outside of those bounds, then we don't quite have that full confidence, because there's a chance that those two don't overlap. So just a couple quick screenshots, same process as before. The only difference is the method chosen here, that there's the confidence interval method. My example is the same otherwise, the 7.5%. And here then in the output, there's just less numbers, I guess, less rows here. We see the standard equivalent interval from negative 4.3 to 4.3, and the alternative confidence interval 0.28, 3.23. So again, visually speaking, you're hoping that alternative CI is contained entirely within the bounds of your standard, which we have in this case. It's near the top end, but it is totally within that. And so again, we have that phrase here where the equivalence is established. So to summarize, if you want to determine that two products or two treatments in your study are effectively the same, you can use an equivalence test. And it's real important, that first step of defining a limit is really the thought part that you need. What difference is inconsequential? What is the appropriate upper and lower bound of what is basically the same? And that's important to define, because certainly you can dream up of the larger you make the limit, the easier it is to have that other treatment land within there. So it's, in some ways, if I go back a minute, some ways, if you really just wanted equivalence, having that limit just be large, you can just make that equivalence range very wide, and then it's not too hard at all for your alternative treatment to land in there. But then you're not really having anything novel by declaring equivalence with such a wide range. So that's why that limit really needs to be grounded in something real about the experiment, about your objective. to make sure that declaring equivalence has meaning, has purpose to it at all. And just like our last function, we do have a presentation that is even more statistical than what I just rambled through. Let me toggle over to that one as well. Pretty similar in structure, covering equivalence tests. Same idea, kind of talking through the theory, and it doesn't take too many slides before we get some hypotheses and then some math for long. But going through a few different examples, and there's some talking about that limit, just like I'd mentioned, that is pretty important too. So if you're not too afraid of some math and textbooks examples, it can be interesting to read through, but it might take a couple read-throughs as well. This is usually what we get first here from our statistician when a new feature rolls out, and it's like, all right, well, I'm going to sit down with this now, and then I'm going to read it again in an hour and see if I can make more sense of it. But slowly but surely, it starts to make sense. Again, showing some examples, kind of proof. Hey, we're matching what other software does, and things of that nature too. Any questions on equivalence tests? Just a couple more minutes. I do have 5 to spare, so I can show a couple of these much smaller changes. But I figured the title here for this session was just statistical changes. So I thought I'd just bring a couple along in case we had a minute or two, just to point out a couple other things that were added in ARM in the statistical realm. Probably the most impactful one here was just within the mean comparisons in your regular AOV report for assessments where your error variance is 0. We tweaked the output just a little to be very clear that no statistics are possible. So when there's no variation in the treatment response, something like no pest pressure, no crop damage, it's all hundreds or all a 0, there's no statistics that can be done there. And so to just make that abundantly clear, the mean comparison is just kind of overwritten as an NA for not applicable, can't be done. And then the statistical output here is not a number, NaN. So just trying to make it super clear that there's just nothing statistical that we can do. The other scenario where this pops up that maybe ends up with a little bit more discussion, just to kind of understand why this is the case. With the same situation of the NA will come up, even if there are differences between treatments, but there's no differences in the response across replicates. So, the examples we'd run into, if you went out and did a visual assessment and you just kind of aggregated, okay, treatment number 2, I'm just kind of spot checking across each replicate to get this visual 10%. So for treatment 4, it's 10%. Well, I'm aggregating that cross replicates, so I have only one value. Or maybe I put in 10 in each replicate, but it's the same value. Well, the result statistically is the same. The error mean square is 0. There's no variation in those replicates, so there's no variation to analyze. So we can't do anything in the ANOVA. So it's the same situation, even though it can be just a little more alarming at first glance. Well, what do you mean? There's clearly differences between my treatments. The response was different depending on what treatment. But if you look at like a box whisker, it kind of helps to show, yeah, but there was no variation here present. So there's nothing to do statistically. And so the key really is to realize, we're putting NA. That doesn't mean there's no significance. We're not claiming there is no difference between these treatments. It's that we can't calculate any statistical conclusion here. Certainly you could claim there's a numerical difference in these treatments, but there's just nothing statistically we can conclude. So that's a small change on the report, a little bit bigger philosophy thing that, again, hopefully is pretty clear once you've seen it, but definitely can be a little alarming that first time it pops up on a report. And just one more minute to go. One last note to make. In the list of mean comparison tests that we offer, that list grew by 1. We added the Scott-Knott mean comparison. This kind of specifically came from Brazil. They have registration requirements to use this mean comparison test. I think the main difference with that analysis is the treatments get assigned to a cluster. And each of those clusters get just a single letter. So you'll notice that there's only one letter in the output for each one. I don't really know the math behind there. There's a likelihood ratio test that goes into that to get differences. And so you still have the same idea. Oops. Still the same idea. If you have like treatment 1 and treatment 5, they're in the same group. They both have the same letter. So it's the same conclusion you can draw in the fact that those two are not significantly different. They're in the same group, whereas 1 and 2 are because they have a different letter. So same outcome, maybe even simpler to read. It's very, very clear you're in a group or not, just one letter. So that is an option in your mean comparison test. And that's all. So that kind of wraps up this session as well as our whole series here this month. Appreciate those of you who joined us today. Again, we'll be sending out the recording later on. Thanks for your participation, and hope maybe we'll see you again in the future.